elasticity, where I define rigorously what is strong form, what is weak form, what is variational formulation of the problem. Then I discuss the basic solution procedures. And then we switch to something called technology of the finite element method. In fact, these aspects of technology is really what is hiding in this computer software that you're using, I'm sure, on a daily basis in your works. And if you really want to modify any of these software, well, this is actually what one has to know and related to that. And after that, we will have a short conclusion. So the philosophy goes as follows. All the problems that we want to solve nowadays are really nonlinear. Linear problems, that means you're talking about Hooke's law, has anyway very limited domain of application and very limited interest in terms of type of problems that we want to solve. And nobody's paying, unfortunately, anymore to solve just a simple linear problem, like used to be the privilege of early works. This point of view that all the problems are nonlinear has been already emphasized by pioneers of nonlinear mechanics, the most famous names Euler and Bernoulli. So today, when people are talking about beam of Euler-Bernoulli, often they talk about linear theory, which is nothing could be more wrong than that, because the real fathers of all this domain, they actually develop a fully nonlinear problem, and then, in fact, the name of Euler is first name related to how to handle a very large rotations, which are not vectors but tensors. So this is topic we're going to discuss a little bit as we go along. In 19th century, that was a very elaborate work of Cauchy, who wrote a book. So then I understood it's good to write a book. Unfortunately, in this book, he linearized everything. So all nonlinear problems that were studied and understood in nonlinear, in 18th century became now linear. And the only, let's say, big achievement of Cauchy, he has modified and defined this in 3D. So at the end, we have a very elaborate formulation of three-dimensional problems for linear elasticity, and many books written in the 20th century and so on. Catalog of problems that can be solved in linear theory. But what really is needed today is how to solve these 3D problems in nonlinear theory. So we follow this path of trying to do 1D like Euler did, and then generalize to 3D. That's more or less the plan. So this first lecture is really all about 1D, just to see how the whole procedure is working. And in 19th century, Cauchy, who was a professor at École de Pont-Chaussée, I had the privilege to be 1 year professor there as well. He has changed his Cauchy, I can tell you. It's not as engineering is not so dominant. It's more like a financial management and so on and so forth. In any case, the idea is that other than this dispute between Cauchy, who was selling hyperelasticity, and Green, who was selling hyperelasticity, turned out Green was actually better, right? Everything was not. And then you need the inelasticity with the so-called internal hidden variables. We'll also discuss this as we go along. Now, in 20th century, there was really lots of work on nonlinear problems. And first, we had so-called qualitative methods written by mathematicians. So in France, the most famous name is Poincaré, who studied stability of motion. And in Russia, it was Lyapunov. What did they decide? That basically instability is the phenomena that can be controlled by a certain quality of motions. In particular, Lyapunov has proposed a functional of Lyapunov that you have to monitor in order to guarantee stability. And this functional happened to be the total energy. So if your total energy is limited in time, in other words, it does not explode as you go along with the motion, then you're sure that you will have a stable motion. So in terms of formulation, the most famous work at that time were Truesdell and Knoll, who developed nonlinear theory of continuum mechanics. These are very famous books, but they have only studied theory formulation. On the other hand, the engineers, they have already studied numerical implementation, and they came to it by a linear theory. So we have works, many of them coming from Berkeley. For example, Yagmai, there was a 1968 thesis at Berkeley that Klaus Jürgen Barthe, who is a professor at MIT in the US now, has generalized, and this was something called updated Lagrangian formulation. What this formulation is basically the idea of taking a small deformation setting and generalizing it to large deformation setting. In other words, if you have like a beam, you can, if you, similar thing for the beam is called co-rotational formulation. So basically, if you have if I can just do it, let me illustrate this. So if you have a for example a beam, oops. So if you have a beam, for example like that, and then you can put a coordinate system along this axis. You can say this is your x-axis of the beam, this is your y-axis, and so on. And then you can have a large motion of this beam, basically by taking really like a large deformation. In fact, the beam itself would be really something like deformed. But you will take again this to be like this will be your axis in the rotating configuration. So basically here you can follow a large rotation. Let me call this what do you call it? Let's say alpha. Yeah, theta, whatever, doesn't matter. This is simply your large rotation story, and these things here are a small deformation. So this is like something that we call the co-rotational formulation, which means large rotation and plus small deformation. So large rotations are obviously this thing here, and small deformation is something like that. So basically, this is the kind of thing that people were using initially. To study this so-called co-rotational formulation. And the same co-rotational formulation dynamics, where you have so-called floating frame approach, where the inertial effects are studied either in a, let's say, global frame or local frame, were taken by Kane in 1976 and then Shield in 2000. So in the present time, 21st century, we are really studying all these engineering disciplines are being connected. So this is really the time of multi of everything. So multi-physics, multi-scale, multimedia, and so on and so forth. And well, you have to live through that. That's the normal situation today. So the illustrative example, I already talked about that as an airplane crashing into these buildings, and you have to time in multi-scale in time. That is, you have to really study impact of the kind of degradation of the plane and so on and so forth. Here's the multi-scale in space. Here's this shaking table type of experiment where you want to understand the behavior of particular structure under earthquake. So typically you have to construct the structure. You can never put a full-size structure because simply it's too heavy. So then you put a small-scale structure and you're doing a shaking table test. This is even more like a small scale. This is so-called nano indentation test, where you have a composite material you put in a machine, and then you're looking into the fracture toughness. That is, you're driving the needle inside this material, and then deciding the property of the structure. So this is definitely when you have a very small scale type of behavior, you want to understand what's going to happen with the large structure. Then this is the kind of thing with the multi-physics, when you have fire resistance in masonry. Basically, you build the structure. This is typical wall. You study what's going to happen for a fire during the 6 hours, and then from that on you extrapolate to see what is going on with this particular structure as we go along. So all these type of things are really motivation. I have already discussed it, and I'm not going to dwell on that again. So what is the goal? First of all, we really have big difficulties of mastering nonlinear mechanics because the solid physical basis is lacking. You have difficulties of interpreting tensor structures. As I said, often you cannot do the full size. Even if you can do the full size, you have to understand that you can measure a vast number of things and have a tremendous amount of information. So if you don't already have idea about the kind of model you want to develop, your measurements often happen to be completely useless or at least incomplete. Of course, the problem you're interested in, which is mechanics, might be affected by many other fields like temperature, like electromagnetics, and so on. So you have this multi-physics. And if you want to be credible in terms of observation of what is going on, you have to go to this multi-scale type of modeling, which is also a big challenge there. Another difficulty is that as soon as you go to this multi-physics and multi-scale, you end up having a tremendous amount of information, and you have a very large computational cost. So these solution methods and computational tools and software is something that needs to be really under control. And today, of course, this is a commercial type of environment, so you have many of these commercial software, so there's always a question of money and license and so on and so forth. Then when you start developing these type of things, you realize that not everything is so easy to compute. There's a robustness of numerical method, which is a big issue. In other words, there's a question of locking, that is inability of our elements to represent some kind of a phenomenon that we are interested in. There's a question of estimating the error in this computation. There's identifying the parameter. There's adapting the model. All these type of domains are current research interests. Then even in linear analysis, if you look into the elements like shells, it is not easy to provide because you have all kind of difficulties like locking and so on and so forth. And finally, my personal experience is, some of the really good software products, often the models which are developed there are excellent, but the pre-processing and post-processing data are not as good. So it turns out that some of the software which actually has excellent pre-processing and post-processing, they actually win in the end. That was the case of CATIA, which was just built for pre and post-processing, and then they made so much money that they could buy excellent codes like Abacus and so on and so forth. That's the way. Sometimes the packaging sells better than the contents, but not always, really. When it comes to hard problems, you really want to have the contents as well. There was of course, a problem with the initiating people who study these type of problems, in the sense that there is a huge number of previous work, and they're getting bigger and bigger, given that we are interested in the interdisciplinarity of these problems. So if you want to study more than the book of that I suggested, my book, you have basically, for example, in the finite element, you have sort of the most important book is by far is Zinkevich Taylor. He has many different editions. But also a book of Taylor's, as I said, one of my former advisors, Zinkevich, was a professor in UK, in Swansea. We also have currently important books, which are Ibn Battuta, professor at MIT. Tom Pusey was at Stanford, now he's in Texas, Austin. Ted Belichko was professor at Northwestern. Or French books, these are my former colleagues from UTC, Guridat and Gilbert Touzeau, Jean-Louis Bartos, Guridat, and so on and so forth. Then if you want to have a books in mechanics, you can have something like Truth and Null, which is, as I said, the most important thing for these theoretical developments. And also Gurtin, Ogden, Marsden, Hughes, and stuff like that. So many of these names will be certainly good enough for you to look at today. You can Google them and get lots of that. In France, the most important works are Jean Lemaitre, Jean-Louis Chaboch, Pierre Ladurez. That was my book in French. So then you need aspects eventually in applied mathematics. Strang is the book that I recommend. It's Introduction to Applied Mathematics. There's also Nuremberg for optimization, Golo, Vallon, Parlet, Tiger, the problem. In France, you have Jacques-Louis Lyons and Philippe Sarnet are the books which pertain to this. Of course, you need functional analysis. So there's really like a large body of knowledge. Luckily, with the book, you can certainly have a little bit better. That was written at the time before the book came operational. So what is the objective that I have in this course? First is to present the theoretical basis, namely variational formulation of problem in nonlinear mechanics, solids and structures, and explain all sources of linearities, and then give you detailed aspects of the finite element method, namely the kind of element type and locking that you can have an operator space solution procedure, programming, and so on and so forth. I will just revisit some of the ideas from applied mathematics. That's not the goal of the course with the matrix computation. And basically, the idea is not only to indicate the problem, but to try to understand what the problem is and learn how to solve it. So let me start with a concrete example. Here I have a three-dimensional problem, which could be like a box, a pen, whatever you want to do it. It has a one dimension much longer than the other two, so that allows us to use a one-dimensional model. Of course, the loading has to be applied in this way. So this could be like a pen in the gravity field. Of course, here gravity field would be horizontal. And basically, when I imagine cutting this into two parts, I can say that the stress is uniformly distributed in the cross section, which is the basically dimensions perpendicular to the length to the axis of this. And then I can use a hypothesis that one-dimensional model is sufficient. In other words, I take that every fiber of this pen behaves in the same way. So I can take a particular fiber, I say the cross-section of this fiber is equal to 1, and I just want to study what happened to this line, one-dimensional model. So what exactly is the study? First, I have to define the loading, what exactly I'm applying. If it's gravity load, so it could be the dead load applied to this structure, I have to define the behavior. So if you start with linear elasticity, the only thing which needs to be defined is a Young's modulus. And then I have to define the domain. In this particular case, this will be length that starts from here to there. And cross-section being 1, I don't have to define this any further. So once I have defined all this, I'm trying to obtain something. What exactly I'm trying to obtain? In mechanics, this is always the same. I'm just trying to obtain three different fields. Fields, that means like a function that has the value that take a particular, let's say, a result from 0 to L, L being the length of this bar. That means that I put a coordinate system in the left hand of the bar, and it goes all the way to the right hand bar, which is at x equal to L. So I have to define the displacement field, u of x, the deformation field, epsilon of x, and the stress field, sigma of x. In order to obtain these three fields, I have to provide three equations. In 1D setting, these are indeed a single equation for each and every of these, but in 3D, it will be group of equations, but in the end of the same nature. So what these equations are is the following. I need kinematics, so that given displacement field, the value of u at any point x, I can obtain the strain field, epsilon at any point x. Then I need constitutive behavior. Given epsilon at any point x, I can provide stress sigma at any point x. And finally, I have equilibrium equation which says that for any internal force, sigma of x, I have to match the external force f of x. Now, these three equations should be defined, and they result in the definition of the boundary value problem. If I want to have a unique solution to such a boundary value problem, I have to specify so-called boundary conditions. These boundary conditions could be either on the imposed displacement, in other words, the component that I isolated. I was talking about the wall inside the building, I was talking about windshield inside the car. You actually specify displacements at certain points of boundary, and the remaining point of boundary, you can specify the stress. That depends what the rest of the structure is doing to your component that you're studying. So the combination of these imposed displacement and imposed stress should cover the whole boundary. Then you have a well-posed problem. Of course, they cannot intersect. In other words, either you impose displacement or you impose the stress. And then basically you can be sure to be able to compute a unique solution to your problem. Here's a very simple illustration. So imagine if I have infinitesimal strain, which is simply obtained as a, in 1D case, as a derivative of displacement field with respect to x. Then I have a linear elastic behavior. The stress sigma is equal to Young's modulus E times deformation epsilon of x. And then I have an equilibrium equation, the derivative of stress sigma with respect to x plus applied loading F is equal to 0. And I apply two boundary conditions. At the left end of the bar, I put 0 displacement, u bar equal to 0. At the right end of the bar, I put the stress, I put the force T, which should be equal to E times du dx at x equal to L. Now, if I put this f of x equal to 0, which is the case here, I can very easily solve this problem and obtain that u of x is equal to x divided by E times T bar. Or the other way around, I can write that the free end displacement, that is the displacement at x equal to L, could be obtained as a L divided by E times T bar, from which I can conclude that T bar is equal to E over L times U or L. If I took cross section anything different than A equal to 1, I would have obtained here E Young's modulus times A cross section divided by L, the length of the bar, times U of L. I can plot this result in a graph which I put displacement to the free end, U of L. So this is actually displacement we are talking about. This is at the free end. And this is the force T bar, which is applied at the same point. So if you put in the abscissa U of L and you put in the ordinate T bar, you can obtain the graph of such a function as a straight line for which the slope, how it is inclined with respect to x-axis, is equal to E divided by L. What you notice in this problem is the following. If you take a force which is equal to T1, you obtain displacement which is equal to U1. If you take the force which is twice as big, you obtain displacement which is twice as big. Hence, these are linear problems where there's a factor of proportionality. There's the same factor that applies to the increase in the loading and corresponding increase into displacement. So these are linear problems that are, as I said, well known nowadays, and have many books which have sort of catalog of these solutions that could be obtained. But what we're interested in is nonlinear problems. So how do you get nonlinear problems? Well, first of all, if you change the constitutive behavior, not only taking linear elasticity like Hooke's law, but let's say you take something like a nonlinear elasticity, in which case the stress sigma of x is a nonlinear function of your deformation epsilon of x. For example, one illustration will be something that looks like a model of the concrete, which is Young's modulus E times epsilon minus epsilon to the power 3. You can see this will be like a linear minus the cubic function coming from here. So the curve stress strain is becoming nonlinear. So with such a curve, if you're now computing the traction with respect to displacement at the end, you're not going to have a linear response. In other words, increasing this force 2 times, you're not going to get 2 times bigger displacement. And even though it is elastic, you still have a nonlinear problem. You cannot use this factor of proportionality, and you have to devise corresponding method that we are going to discuss as we go along. More interesting problems than nonlinear elasticity, more closer to really industrial applications that we're interested in, are basically this inelastic behavior of material. For example, if you take plasticity, this is typical result of a test that you have in the testing machine. In other words, what you see, this rectangular shape, it's an initial configuration of some kind of steel specimen, only half of that is pictured. And this curvilinear shape is the deformed configuration. Typically, you have a specimen breaking in two, so I just picture half of it. And this breaking is related if you take a material like steel or aluminum with the phenomena like necking. In other words, the section in the middle of the wire starts being reduced and it breaks. And you still want to describe this with one-dimensional model. If you do that, you not only need to define how the stress depends on the total strain, but you also have to introduce the notion of the plastic strain. In other words, when you go beyond the limit of elasticity and you start hardening, if you will go to unloading, you're going to recover strain which cannot be removed, which is a permanent irreversible strain that stays in the elastoplastic material once you've crossed the limit of elasticity. And of course, the fact that once you cross the limit of elasticity, material still can resist, this is called hardening, then you need another variable called hardening. So not only that you need more variables to describe the behavior and obtain the stress from the given strain by supplying also so-called internal variables, you also need, let's say, a better representation than truly one-dimensional, because this necking phenomena obviously indicates that one-dimensional case cannot represent, because here there's no necking, here there's a very severe necking. So obviously, if you want to be credible, you cannot simply stay with 1D model. But sometimes, people do it in a simplified way, because that allows you to give a first estimate of the phenomena which are being studying, and basically 1D case will be just fine enough. So here's the sources of nonlinearity, either nonlinear elasticity or elastoplasticity, where the main source of nonlinearity is the constitutive behavior. You can also have a sources of nonlinearity where the main source of nonlinearity is the kinematics. In other words, if you take a specimen and you now stretch it very large manner, for example, this would be possible for a rubber type of material. And often for this one, what is recommended is the model of Ogden, where basically, if you want now to measure, if you stretch it 2 times and this is still not breaking, obviously you have a nonlinear kinematics. Now, rubber is often considered to be incompressible material. Water is also considered to be incompressible. What that means is the deformation that leads to change of volume is much, much smaller than deformation that leads to change of we really talk about incompressible. So that means if the initial configuration, which is this rectangular shape here, should be the same as the form configuration, again, you should have thinning of the cross section because the volume of this, let's say, deformed here configuration should be the same as the volume of the initial configuration. What you get is the typical result for the displacement at the free end under the applied force, which is called T bar. First, rubber starts hardening and then softening and then hardening again. The more you stretch it, the harder it gets until it breaks. So obviously, when you take a T1 and you get displacement U1, multiplying this T1 by 2 is not going to get you 2 times as big displacement. But so again, this is nonlinear problem. But this time, nonlinearity is due to nonlinear kinematics. So the final one is the boundary condition. So imagine if you had a simple linear elasticity problem and you apply your force T, so there you're linear, but at a certain point here you have an obstacle. So instead of saying that the obstacle is rigid, sometimes I can say that the obstacle is something like a very strong spring that comes in the way and not let this guy expand freely. So once the bar, which is being extended, comes into contact with this spring, then together bar and the spring are resisting any further increase of the loading. So instead of having this slope, which is only E over L, which is the stiffness of this bar, you have now the slope, which is K plus E over L, where K is the stiffness of the spring, representing the obstacle. So basically, it becomes much stiffer. So if your T1 is here, and 2 times T1 is there, obviously that U1 and U2, 2 times this is not 2 times U1. Again, it's not linear problem. It could be linear piecewise, in other words, by one phenomenon or the other, but globally, it is certainly not linear altogether. So we'll study all these type of things, and I'm not going to follow this type of, let's say, plans. I'll skip these 2 transparencies very quickly and go further. So my first goal is to obtain the theoretical formulation, giving you strong, weak, and variational problem in one-dimensional case. And to do that, I'm going to study simultaneously 2 different problems. One is the linear elasticity, and the other one is nonlinear elasticity. So for linear elasticity, this is let's say this body which is loaded in the direction of the axis of the body, so that I can provide a one-dimensional model of this body, and I can study how the, let's say, free end displacement behaves under the imposed force T bar. So for the linear elasticity case, you already say that we already said that there's going to be factor of proportionality, so 2 times bigger force will produce 2 times bigger displacement, and for nonlinear elasticity, that's not necessarily the case, and we'll see how we deal with such a problem as well. So first of all, we define the domain. Given that we have a one-dimensional problem with the cross-section A equal to 1, so we don't worry about cross-section anymore, we can actually define the domain simply by assuming the x-axis is placed in the left hand of the bar. So the domain is all the values of x that span from 0 to L, where the L is the length of this bar. Hence, the boundary reduces only to 2 points. Often this is called 2-point boundary review problem. So this is either with x is equal to 0 or with x is equal to L. So when you apply, for example, displacement at x equal to 0, in other words, you put a support at this point, you can call this so-called Dirichlet boundary. That is gamma u, gamma being the boundary, u indicating the displacement field. Then you imply the force on the right-hand side for x equal to L. You have so-called Neumann boundary, gamma sigma, where you actually impose this force that sigma of L is equal to T, given that the cross-section A is equal to 1. So the domain omega being the inside of the interval from 0 to L, and the boundary containing these 2 points x equal to 0 and equal to L, they together denoted as omega with the bar. In other words, this is like a complete domain, including these 2 boundaries. For a well-posed problem, we require that gamma u and gamma sigma cannot be the same. In other words, this is an empty set. And on the other side, we require that gamma u plus gamma sigma constitute the whole gamma. So we have to define what happens at x equal to 0 and x equal to L, and either in every of those points you apply displacement or you apply stress. You cannot apply both. So if you respect all these, you also have to define your external loading. For example, I'm going to call this B of x, like a body force. Typically, this is representative of the dead load for this structure. And then you will have a imposed displacement as well as imposed traction. So this is full picture of all the imposed loads that you can have. Now you need a geometric characteristic. These are length of the bar and cross section. I'll keep taking A equal to 1. At the end, I can bring it back not to be 1, but that's really the main thing in formulating this problem. And then final set of data is how the material behaves. Since we started with the linear elasticity and nonlinear elasticity, for the first one, I just need Young's modulus E, and for the second one, I need some law which specify how the stress sigma could be computed as a function of the deformation epsilon. And then once I have defined all this, I need to get the solution for the unknowns. What unknowns are, this is displacement field U of x, this is deformation field epsilon of x, and this is stress field sigma of x. So how do we construct this? Well, as I said, we have 3 sets of equations: kinematics, constant equation, equilibrium, as we go along. So first, kinematics. When we have a small displacement gradient theory, that means if you follow how the displacement changes, and changes is given, take the derivative of displacement field u with respect to x, because if u is function of different values along the x, along the length of the bar, the derivative du dx will give you how this change is happening. So we study only very small displacement gradient. That means the value of du dx for every value of x between 0 and L has to be much, much smaller than 1. Typically, you're talking about, let's say, a steel structure. Steel structure has a yield, that the deformation when the yield starts equal to 400. So, and the Young's modulus, 400 megapascal, if it's good quality steel. And the Young's modulus is 200,000 megapascal for a typical steel. So the deformation field this is 2 10 to the minus 3. This is 002. Sometimes to see that you actually have deformation. So this is what you call a small displacement gradient theory. And basically, you can say why the deformation, something like du dx, is basically by saying that if you have displacement point x, if you look into displacement at point x plus dx, where dx is very small, could be 10 to the minus 5, you can take a Taylor's formula to develop what is u of x plus dx as a value of u of x plus the first derivative of x times dx plus 1/2 second derivative of x times dx squared plus all these terms of the higher order. So what we'll do is basically first recognize that if u of x is the same as u of x plus dx, then basically you have like a derivative has to be, all derivative has to be equal to 0, and you have something called rigid body motion. If the whole bar at every point of x has exactly the same displacement, it's simply not deforming, it's just moving as a rigid body. What we're interested in is really to get deformation. So what we do here, we say we're going to take a first gradient theory. So we're going to neglect the second derivative. We say this is equal to 0. This is only done when you have some kind of no local theory, which is not the case for us. And then also you can say that at the end, the difference between u of x and ux plus dx is now brought by deformation. So what the difference is, obviously, is just proportional to the du dx. Hence, the justification why the infinitesimal strain is equal to du dx. That is, the change of displacement as we move along x is equal to this infinitesimal strain. Now, as soon as we realize that these infinitesimal strains are very small, we can, in other words, that this is much, much smaller than 1, we can use this to simplify the further development of the equilibrium equation. In other words, equilibrium equation with the stress, this is called true or Cauchy stress, should really be developed in the deformed configuration. However, if the strains are infinitesimal, that means that this deformed x is almost like the same as the initial x. Then every time we compute derivative with respect to this deformed x, here I call this x with index phi, we say simply replace it by derivative with respect to x. And so integration over the deformed length L phi, this is so close to L that we can simply replace it by integration over L. Hence, we can now set equilibrium equation on the part of the bar where we apply the stresses at x plus dx and the stresses at x, the difference of those two multiplied by the cross section for a equal to 1, you don't have to worry about that one, should be equal to all the loading which is applied to this part of the bar, which is equal to distributed loading d of x times the length of this infinitesimal element, which is dx. Hence, if I now divide this by dx, I'm going to get something which is representative of the relative of sigma with respect to x, which I can prove by using the Taylor's formula here. And finally, from this equation, I can conclude that the equilibrium equation, which could be simplified thanks to the small displacement gradient setting, should be written in the initial configuration by using true or Cauchy stress acting in deformed configuration. And you can say that the derivative of sigma with respect to x plus b is equal to 0. This is the major difference when you go to large deformation setting. This x will no longer be x in the initial configuration, but will be x phi. And then brings all the complexities we're going to be talking about as we go along. Final piece of information is the constitutive behavior. Consider that we have either a linear elasticity model or we have a nonlinear elasticity model. So we can have like let's say for linear elasticity model, sigma is simply product of Young's modulus E times your infinitesimal deformation epsilon x. Whereas for nonlinear elasticity model, sigma is a nonlinear function of x and epsilon x. If you have homogeneous material, these two simplify, that you don't have to worry about these parameters being dependent on x, so you just drop x from this type of expression. So sigma is simply equal E times epsilon x, and sigma of x here is simply always the same for any x. So when we take these three equations, so first of all, by using kinematics, which is epsilon equal to d udx, and using to start with linear elasticity, I can obtain that sigma is equal to E times du dx. And then I take this one and I include it in the equilibrium equation here, that sigma being E times du dx, considering that D is constant, I can finally obtain this is E times second derivative of u with respect to x plus b equal to 0, which is this equation written here. If I have nonlinear elasticity, I will have to get this in terms of nonlinear equation, which I cannot write explicitly. It depends really what kind of equation you want to apply, but still going to be derivative of the function of sigma, which is now directly a function of u. That is why I'm not calling it sigma head, but I'm calling it sigma tilde plus b equal to 0. Let me stick with the linear elasticity. Obviously, this is an equilibrium equation expressed now in terms of displacement directly. I have obtained this equation by combining kinematics, constitutive, and equilibrium equation together to express a single equation of this kind. You can see that this equation is the second order differential equation with the second derivative of displacement field with respect to x featuring in this equation. So it is logical that if you really now want to compute the solution to this equation, you can integrate this 2 times. In the process of integration, you're going to have like 2 integration constants, and that is why you need 2 conditions from which you can compute these constants. These conditions happen to be precisely the boundary conditions, either on imposed displacement or unimposed stress, which allow you to compute these constants uniquely, and this way you have a unique solution to a problem. So when you talk about strong form or 1D elasticity or strong form any formulation mechanics, it simply means that you have actually obtained a single equation which represents equilibrium equation of a particular problem. Here is 1D elasticity, a small displacement, expressed directly in terms of displacement field. Analytical solution of this problem is rather easy. Depends what you put for B. If you put B constant, obviously U will be a quadratic polynomial in X, and so on and so forth. And what is really important to note is the regularity of the loading is imposing a regularity of the function U. In other words, if you want to have a function U to be in the set of functions which is called C index K, what that means is that this function is continuous and all the derivatives up to order K are continuous. But if you have then load should be in the order of K minus 2. Let me just give you for a brief second illustration of what that would be. So if I take a application of this type, and I want to illustrate what happens here. It is basically if you have a truss bar element, let's say, and I'm saying that this truss bar element has some displacement which are U1 and U2, and I want to obtain something which is, let's say, linear interpolation of the displacement field, which should be something like this. Well, there should be all straight line, but I didn't take this one option. So this is your U1, and this is your U2, and this is your U2. Oh. So I can write here that, let's say, U1 of x, U of x is equal to, let's say, 1 minus x over L times U1 plus x over L times U2. So this is my U. After that, I can say that my epsilon will be equal simply U2 minus U1, all this divided by L. And that means this is a constant L. Then my sigma will be equal to E times epsilon, which is equal to, let's say, constant as well. So basically, if I have such a model, and this is the model which is simplest, this is simplest two-node truss element. Now, conclusion, you cannot represent exactly equilibrium equations for B except for B equal to 0. In other words, if you take such a linear formulation for displacement field with epsilon and sigma being constant, if you take derivative, then you will have a d sigma dx plus b equal to 0 when only if you have a b equal to 0. So this is very limited choice if you think of that, of such a model. But again, this is what we can do when you have a strength form. Well, we still want to get a weak form. This is another way of representing. And the problem is here in 1D, it's very easy to integrate. But in the more general case, 2D, 3D, I mean, there are books and books written simply because your presentation of the boundary conditions is very complicated. And obtaining such a regularity of the displacement field is not easy. So we switch to something called weak form, where the goal is to reduce the highest order of derivative which appears in this formulation. We go from the particular case second order to the first order. How do we do that? Well, we weaken interpretation of equilibrium. In other words, instead of saying that equilibrium is such that at every point x, the second derivative displacement field times E plus B is equal to 0, we say, no, we're going to be happy just if we integrate this over the whole cross-section. Sorry, not cross-section, over the whole domain, which is the length from 0 to L. And then we hope that, let's say, the integral, that means the sum of all these stresses acting the bar, should be equal to the load that we apply. So basically, this is the basis of any finite element solution software. So what does that mean practically? It means in this finite element computation, the only solution which is exact, even if you use the simplest model like the trusses and bars with two nodes, the only solution which is exact should be the reaction of the supports. In other words, by using this, you can say that the total loading is matched, total external loading, let's say, the dead loaded structure is completely exactly matched by the reaction, but nothing else really, just that part there. So is that an advantage? Well, certainly not. But on the other hand, this gives you all the chances to see how to solve the problem in the case where you only have a first order derivative, and also gives you a chance to be like an expert who can say something is right, something is wrong. So definitely you can find the solution more easily when you switch to this weak form of the problem, where everything is just integrated along the domain. So here you have in the linear elasticity. Now we are looking into the solution, which could be if B is C minus 1, which could be in C1, whereas the weak form would allow us a solution which is H1. What does that mean? If I go back to my whiteboard, typically if you say like a solution which would be in C1, solution which would be in C1 would be something like that. I would have something that is continuous, and the first derivative should be continuous. So you have something like let's say here's a positive, this is after that is negative, and this is positive again. So say this is your function u, and this is your function du dx. Du dx. Okay, dx. And this is something needing for the strong form. On the other hand, I'm looking to replace this by something which could be used for the weak form. Oops. Let me just remove this. Not good. Let me try to do it better, like this. So with the strong form, with the weak form, I can have this, and then I can have, oh, and then I can have this. Okay, and then I can have this, and then I can have this. So basically, if this is also my u, okay, let me just write first what I have here. I'm going to have a positive value here, then I'm going to have negative value here, and then I'm going to have a positive value here as well. Of course, these are all connected like this and like that. So now this is my u, and this is my du dx. And this is used for the weak form. So you can see that it is much easier to construct a function like that in the process of the finite element than a function like that where you need lots of continuity in order to fulfill all the conditions. And that's really what we're after. So basically, let me go back here. So I'm going to do this weak form, which means integrating over the length of the bar, and basically then taking integration by parts. So what I obtain is the following. I integrate this. I need to multiply by some kind of weighting function. So it's not only that I'm integrating, but I'm actually using a weighting function which is averaging this result over the length of the bar. And then I do integration by parts, and I can show that the strong form could be replaced by the so-called weak form. Here's the for linear elasticity, where you have a stress E times du dx multiplied by so-called weighting deformation dw dx, and should be equal to minus wb plus here w times the t at gamma sigma equal to 0. For nonlinear elasticity, you would get this type of expression to combine with. So can you say that these two are equivalent? Normally, yes. If you start with the strong form, you go into the computation by the weak form. And so basically, I leave you this as a small homework, how to show that these two are equivalent. Basically, what you need is simply when you multiply this by a weighting function, you need this result which comes from the integration by parts. That is, the derivative of the product of these two is equal to the derivative of the first times the second plus derivative of the second times the first. And then basically you integrate over that and you get the final one with the saying that the integral of the derivative of W sigma comes down to W sigma times n being the unit vector exterior normal. It's either plus or minus 1 for this 1D case, and that actually brings you back to this condition there. That means that the strong form is always equivalent to the weak form. In other words, if I have solution of the strong form, I can always obtain the solution of the weak form. The inverse direction is not true. In other words, if I have a solution of the weak form, I have to make sure that the regularity of the stress, which is not required in the weak form, happens to be true. In other words, that you have a high regularity, which was then what was required to start with, so that the derivative of sigma is squared to x can give me back my some meaningful result. And that way I can show that the weak form actually comes down to the strong form. In other words, I recover something like equilibrium equation d sigma dx from the governing statement of the weak form. And on top of that, I recover interpretation of what is here the boundary condition of the imposed stresses. In other words, I can say that sigma n is sigma times n is equal to t bar. Hence, this boundary condition is so-called a natural boundary condition. In other words, you recover this naturally from the particular statement of your weak form. And the other guy is called essential. In other words, that u is equal to u bar is essential. It has to be present both in the weak form and in the strong form. So this is the conclusion that these two forms are equivalent, but the weak form has the ability to provide the solution, which is, let's say, easier to construct because it does not need the same regularity. It just needs a function just square integral. There's another name for this weighting type of residual approach that I just explained. What is the weak form, what is the strong form, because W here is called the weighting function. There are other two names of the W that I want to briefly recall. One is the W is called the virtual displacement. So the weighting function being virtual displacement, that gives to the weak form interpretation in terms of work. In other words, you can say that the principle of virtual work states that the work of the external forces should match the work of the internal forces if the body is in equilibrium. In other words, if you want to obtain if the particular configuration of 1D bar, which is loaded by some kind of loading, is in equilibrium, you imagine you apply a virtual displacement. What this virtual displacement should do, well, in 1D case, it can only go along the x-axis. And so you can then establish the work of the internal forces, which is basically sigma times dx and multiply dw dx, which is basically virtual deformation. And you integrate contribution of all these sigmas along the bar. That means from 0 to L. On the other hand, you have a contribution of the external loads. This is distributed load B times dx times the corresponding displacement W at particular point x. You integrate from 0 to L. And on top of that, you have this contribution of the applied traction. Let's say the boundary gamma sigma, this is here what I discussed for the value of x equal to L. So if these two values match, that means you have an equilibrium. So basically, then you can say that the internal and external forces are matching. What's important to say, if I use gamma u at this particular point, I impose displacement u bar. It doesn't have to be zero. My w, on the other hand, has to be equal to zero. So the virtual displacement has to be so-called kinematically admissible, giving that at the time where I know the real displacement, at the place x, where I know real displacement happen to be here at gamma u, which is for x equal to 0, I have to impose the virtual displacement w to be equal to 0. The third name, so you have a name which is weighting function, you have a virtual displacement. The third name is so-called variation. This is, in my mind, one of the most beautiful chapters of this mathematics. It is related to calculus of variations. There are many good books on that. My favorites are Hildebrand, is the first one who actually made a crucial distinction in terms of notation. What is this small symbol delta that you'll come across, as opposed to like symbol of variation, as opposed to a symbol of derivation. And then you have many others who are more recent, and so on and so forth. Now, what is this principle about? Basically, this principle starts from the level of energy, because now you actually take the whole energy of the particular bar. You define the energy as the internal energy. Here we are talking about hyperelasticity, in which case the stress is sigma of x could be computed as the partial derivative of w with respect to epsilon. So for linear elasticity, it's very simple. W could be 1/2 epsilon times e times epsilon. So when you compute derivative with respect to epsilon, this quadratic form, you get that sigma is equal to e times epsilon. And then external energy is computed by multiplying the applied loading B with the displacement U, as well as the applied traction T with the corresponding displacement. Here is U of L. So now the goal of this calculus of variation is what? You have a so-called functional. This is not the same thing as function. U of x is a function. In other words, for every value of x, from x going from 0 to L, you have a displacement field, which is a function of x, and you give a particular value to this function. Now, P is a scalar value. It's a total potential energy of this bar. And it is actually computed as in terms of the argument, which is the whole function u of x. So if you think of that, functional P of u of x is a function of a function. So u of x is function, and P is a function of this function of x. And so how do you compute the minimum? Because this is the principle of the functional. So for function, it's easy. A function f of x is defined. This is illustration of it. You can say that the minimum is decided by two conditions. First one is that the first derivative at the particular point where minimum is, which we call x bar, should be equal to 0. And the second one is that the second condition is the second derivative at the same point x bar should be positive. So in this way, you know that you're increasing the value either if you go left or if you go right. So these are two conditions which are sufficient and necessary sufficient to obtain the minimum of this function. So, but what do you do in terms of functional? Well, functional is a little bit more complicated. You cannot use something called the Frechet derivative, like the case here, but you have to compute something called Gatto derivative. Let me just illustrate this again with this kind of illustration. So basically, the idea goes as follows. Let me erase all this. If this is, well, maybe I can do it here. If this is displacement field, I can say that on top of this displacement field, I can apply a small perturbation field, which I can call W. You can notice the W at this point where I apply the support. Here I can say the W of 0 is equal to 0. This is this idea of kinematic admissibility. And any other point, I have this variation. So these two together, they can construct something called U alpha of x, which is equal to U of x. This is the true solution that I'm trying to compute, which I don't know, plus alpha, a small parameter, times variation W of x. And again, this variation W of x has to be kinematically admissible, which simply means that at the point where I apply the true displacement, this U of alpha has to be equal to U bar. So this is kinematic admissibility. U of alpha at 0 should still be equal to U bar. So this is the kind of thing that you can, that means the W of 0 here has to be equal to 0. And that's this kinematic admissibility. So basically, if I go back to my presentation, I can then construct this type of derivative. See here, I have my, well, here I call it a little y epsilon. Sorry about that. Alpha was the symbol probably, but it was before because there was a reason to confuse this epsilon with the strain. This is not the case. Epsilon here is a small parameter. And then I can construct derivative of so-called Gatto rather than Fresche, where I take a U, which is an unknown solution I'm trying to find, plus variation W, multiplying by this small parameter here is epsilon, which should have been alpha, and then I divide everything by alpha. And so taking this to limit process where alpha goes to 0, I obtain something from this functional, which is precisely the weak form of my equilibrium equation, or if you want a principle of virtual work. And I have already seen that this is equal to 0 because that's the principle of virtual work. So the first condition that the first derivative is equal to 0 is already fulfilled. Then I take this result and I do this process of constructing Gatto derivative again. In other words, sigma is equal to really E times du dx, and I get variation of the EUX, and I can obtain that the second derivative simply becomes dw dx times E, which is Young's modulus, times dw dx. Or rather, if it's non linear, it should be C instead of E, C being the tangent modulus. So I can see all the time, first of all, if I exclude that the W of x of 0 is equal to 0, that excludes the value of W being constant, because otherwise you would have this fulfilled. So for any W which is kinematically admissible, this dw dx is strictly positive. So dw dx, I mean, squared is strictly positive, c is strictly positive. So in other words, I have second condition, which is here that the second variation, second derivative is positive. Hence, I have shown by virtue of the virtual work principle or by weak form of equilibrium equation, and also the second derivative disappearing, that I have these two conditions for the minimum. In other words, if I have the form configuration with the real displacement field equal to U, and then I imagine a small bird coming to perturb the configuration, adding this small perturbation W times the parameter epsilon, then I can develop this in a Taylor series to say this is equal to the first variation plus 1/2 here is missing, times second variation plus the terms of the higher order. Now I have just shown that this first variation is equal to 0. Second variation is always positive, which means that the energy in the perturbed configuration is always larger than the energy in my true deformed configuration. Hence, I can really this way guarantee that I have minimum or total potential energy. So this one is really the most powerful part, because this way I can really have a, what you call it, a principle of the minimum potential energy, which is obtained. The fact that weak form is also used for some proving the social existence in the uniqueness is also something that could be consulted in many of these books on functional analysis. What I'm going to say for all those who are working on the heterogeneous materials, what you really need is that your internal energy be bound from above, that is never bigger than a certain value, and from below is never smaller than a certain value, and then you're sure that you have guarantees for a meaningful solution of your case. So let me now go to, after it presented strong form, weak form, variational form, and 1D elasticity, let me now go to some of these basic solution procedures. First of all, we're going to construct this solution by using, as I already showed, let's say the simplest case of truss bar element by using some of these shade functions multiplied by the parameters U of A. So this way, I'm doing actually the modeling. I'm choosing what would be the variation of displacement field in the approximate manner. That is why I need this H being introduced everywhere, because now I'm switching from any function u of x to be the solution of my problem to a function which is constructed as a linear combination of so-called shape functions that are chosen interpolations to be used in order to obtain this solution to the problem. Typically, these shape functions are polynomials in finite element method. And today you have more and more these other type of methods, like, for example, a colleague of mine, Pierre Villon, who is now retired, he has used the so-called diffuse approximation, where you can have a other type of functions. Or for example, nowadays it's if you look into many papers written by Tom Hughes and the people who work with him, they have something called isogeometric elements, where these shape functions are rational Bezier functions that are used in computer graphics. For him, the argument was that it's better to use these functions from the computer graphics, because computer graphics is much bigger industry than finite elements, because you have these guys like Pixar and everything else. So we might as well adapt to them. But the problem is not so simple. It's not only adapted to people who have more money. Of course, this is the principle universal nowadays in the world. But the idea is really that you need a guarantee that the solution could be achieved. So the reason why the finite element actually work at the end is the following. If the solution to your problem in terms of mathematics is so-called analytical function, that means you can always develop the value of this function by using Taylor series, using the value at particular point of the function of this first derivative, second derivative, so on and so forth, then you're sure when you use the polynomials, basically you come down to using the Taylor series directly. And then you're sure that you can converge intuitively. Whereas if you have some other functions, you're missing so-called completeness. You're not sure that all these functions can lead coherently to representing the Taylor series. Hence, let me stick with a very simple type of illustration, where I'm going to introduce the approximation, which is in terms of the known shape function. So you're the one who's choosing the shape function, thinking what's the best model to be used. But so if you take a linear shape function, that means you're taking a two-node trust bar element. If you take a quadratic, that means you're using three-node trust bar element. We'll talk about that as we go along. As you choose these shape functions for the real displacement field, you also have to choose these shape functions for the virtual displacement field. And typically in the Galerkin method, the Ritz method that we discuss here, you choose the same shape function like this. Basically, that's the reason, because the problems, elasticity, heat transfer stuff, are so-called elliptic problems. And the best thing you can do is basically choosing these shape functions to be exactly the same. That really gives you preserves the symmetry and so on and so forth. So what is now the solution procedure? When I use this application, I'm basically taking this to be that I have the function here replacing the weak form. In this case, everything becomes known rather than these parameters that are multiplying the displacement field. They are the only unknowns, but everything is now defined as a finite dimensional approximation, and you have still a weak form to be satisfied. If you take the same approximation and you introduce this into the total potential energy which you want to minimize, then you actually end up having a Ritz method. So what is one, what is the other? Here's the illustration. Imagine I have here the whole domain split into a number of these two-node elements. And for every of those elements, I construct a piecewise linear shape function n of x. Now, you can have a global point of view, like the point of view of Galerkin and Ritz, where these functions are constructing over the whole domain. And basically, then you can say that u of h is this function na of x times ua. If you choose this type of construction, the value of this function na of x at every node a is precisely equal to 1. So at na plus 1, at node a plus 1, this function is again equal to 1. And to all the other nodes, the value of this function is equal to 0. So these are little hat-like structures that are constructed all over the place. So for this particular case, you can be sure that this ua are nothing else but the nodal value of the displacement field, and it gives you like a physical interpretation of the computed result, which is certainly much more meaningful when you're trying to obtain some kind of a good result. So this is really the easiest type of approximation I can imagine, that is based on top of the two-node trust bar element, where you actually have a global point of view in constructing your structure. So what do you do then? Well, you then introduce this into the weak form of your equation, and you realize that the weak form of your equation or virtual principle could be written as the nodal values of the virtual displacement multiplied by the residual. And residual is the product of the components KAB times UB, where UB are nodal value of the displacement of the real field, and KAB is so-called the components of the stiffness matrix. The stiffness matrix is a notion that you have studied if you ever looked into any structural mechanics course. It's a matrix that depends only on the geometric and the material property of the structure, and that is characterizing the behavior of the particular structure. So this F, on the other hand, is so-called equivalent nodal load. Please note that it does have a function, it has a dimension of the loading, but physically it does not represent the loading only. It represents mostly the corresponding work that is forces like P bar and B are acting in terms of the chosen virtual displacement. So basically choosing the virtual displacement gives you the quantification, how these loads are really acting upon the structure. So it's not the same like if you have one load or another load, it really gives you the kind of a different interpretation of this kind. Hence, the reasoning goes as follows. If I say that the product between all these WAs and RAs has to be equal to 0, then I can argue after that these WA, these are virtual displacement, and other than making them my previous illustration. See, basically I can have here for every node variation of this W to be chosen arbitrarily. The only one which is not arbitrarily is W of 0 is equal to 0. All the others are. So basically, if I go back to my equation here, I can say that all these WAs could be chosen anything I want, and still result should be valid. How does this possible? Well, the only way this could be possible if RA is equal to 0. In other words, then you have that KAB times UB, sum of all these B's, it has to be equal to FA for every value of A equal to 1, 2, and so on for all the free nodes. So basically, the end result of this Galerkin or this procedure is basically a set of linear algebraic equation, where here you have a stiffness matrix of a particular structure. Here you have the value of nodal displacements, which are unknown, and here you have an equivalent external load, which is nothing but interpretation of the virtual work of your true applied loading. So this is always the last product of the finite element computation in statics. You have a set of linear algebraic equations. And now you have to be able to solve this set of linear algebraic equations. So the methods, I'm sure you've studied more than one. There's Gauss elimination. There are iterative methods like Jacobi, Gauss-Seidel. There's higher methods like conjugate gradient and so on and so forth. So despite the fact that we have had this problem on our hands for a very, very long time, we still don't have a perfect method where we can actually solve this set of equation. But it doesn't matter. If it's small enough, you can solve it in a very nice way. Okay, once we solve this set of equation, it means I compute the nodal values of U, given that I know a stiffness matrix. As soon as I know geometry and material properties, I can compute stiffness matrix. It doesn't have to do nothing with loading. Then equivalent nodal vector has to do with the loading times the work of this load in the virtual displacement. And then given K and F external, I can compute the values of U. Once I have U, what do? Well, I finish the computation. First, given U, I can compute displacement field everywhere. And then I can compute deformation field everywhere simply by computing derivative of such a displacement field. So that comes to computing the derivative of the shape functions times the nodal value of the displacement field, which I just obtained. In this particular case, where I had a two-node trusses, the shape functions are linear, so their derivatives are constant. In other words, for each and every element, I have simply constant strain interpolation. And then I multiply this by Young's modulus for linear elasticity, and I have stresses. Or if it's nonlinear elasticity, I multiply it by this, and this is all. So now if I have a nonlinear problem, the procedure is the same. The only thing which gets complicated here, the strain field is still B times U, the sum of all these three nodes B, but now it's a nonlinear function of the strain, the internal force that I have to compute. In other words, the stress itself is nonlinear function of the strain, so the strain is computed here. This is nonlinear function of my strain. And here is the coming from the virtual displacement, let's say, or virtual strain, which displacement rate or virtual strain, this coefficient BB. So in this particular case, I don't obtain a set of linear algebraic equations, but for nonlinear elasticity, I obtain a set of nonlinear algebraic equations. And then it's the goal to obtain something called incremental analysis and stuff like that to be able to show how you actually compute and solve such a problem. In other words, here in the matrix notation, you have all the internal forces matching the external forces. Now, please remark that in the linear elasticity, these internal forces are simply stiffness matrix times the nodal value of displacement field. So the equations are still the same, either linear or nonlinear elasticity, only that for the linear elasticity, these internal forces are proportional to the nodal value of displacement, which is not the case for the nonlinear elasticity. But we will show that we can solve the nonlinear elasticity by using already to do for the first homework. Imagine now if you have a simple example where you have a single bar, a single element, which is of the length equal to L, and it goes with the imposed displacement U bar and the imposed traction P bar, and on top of that you have a constant loading B. So I want to solve this problem for two cases. One when it's have a linear elasticity, and the other one it has nonlinear elasticity. So let me try first to solve this for the strong form. Hence, I recall that in strong form, I have a kinematics that epsilon is du dx. I have constant equation sigma is equal to E times epsilon, and I have equilibrium that d sigma dx plus d is equal to 0. Combining these first two equations, I obtain that sigma is equal to E times du dx, and then plugging this into the equilibrium equation, I have this E times second derivative u with respect to x plus d equal to 0. Now, I can solve this equation by choosing particular boundary conditions that I discussed up to now. There's left hand of the bar is fixed and impose the value of displacement u bar. Right hand is applied the P bar. That means that the stress at L, which is equal to E times du dx at x equal to L for the linear elasticity is equal to P bar. So integrating first equation, equilibrium equation, which is here, I obtained that du dx is equal to minus b over e times x plus c1. I can use now the boundary condition on the imposed forces, and from this one I can obtain this coefficient c1 should be nothing else but p bar plus bl divided by e. I can put it back here, and this becomes my expression for the first derivative displacement field. What is that? Well, this is the strain field that goes along the bar. You can see that this strain field happens to be linear in x, and depends on all these loading P bar B, as well as the properties like L, E, and so on and so forth. Now, multiplying the strain field by the Young's modulus, I get by definition stress. And you can see the stress is equal to P bar plus B times L minus X. If you studied this type of problem, you can imagine cutting a part of the bar at distance X, and you can reverberate this way the stress is sigma X, and you can see that sigma should be equal to all the stresses, all the loads applied to the right on this section. And so these are P bar plus B times L minus X, which is precisely this expression for sigma. So this is confirmation that we actually have done correct result for the stress field. Now here was a mistake, and I asked you to check this with the homework to try and find the true exact solution. This one is wrong. On the other hand, U of L is right, and I at the end have U bar plus PL divided by E plus BL squared divided by 2E. Now, this is the solution of the strong form. I want now to obtain the solution of the weak form. I'll go very quickly because you're going to try this to do your homework. So what do? I take a virtual work, which is internal forces sigma times the virtual deformation, which is dw dx. I integrate over 0 and between 0 and L. And I compare this, I match this with the external work, which is W times B dx plus W of L times T bar. And then I choose the linear interpolation because I have only one element. So basically, I take a shape functions to be 1 minus x over L for the first node and x over L for the second node. That's precisely what's written here. So this is the shape function N1, 1 minus x over L times W1. And then you have a second shape function, which is x over L times W2. So I use this interpolation to construct virtual displacement field and real displacement field. The only difference, the shape functions are the same. The only difference, the nodal values are not. Then I can also apply the, let's say, boundary conditions. In other words, I can say that at the left hand, my displacement field is known. That would imply that U1, I already know what it is. It's equal to U bar. Hence, my total displacement field could be at the end written by applying boundary condition as a UH of x is equal to U bar, the known value, times 1 minus x minus divided by L, plus U2 multiplied by x over L. And I also know the kinematic admissibility implies that W of 0 has to be equal to 0. That means now that W1 has to be equal to 0. So from this interpolation of the virtual displacement, that W1 is equal to 0. I'm left only with W2 times x minus L. So now I use these two interpolations for U and for W into the weak form, which is given here. I integrate, and this is what I obtain. So this is the d over dx of the shape functions x over L, e times d over dx. Here is the total expression for displacement, depends on U bar and so on and so forth. These are the shape function for the external forces, shape function multiplied by the applied load, so get the equivalent external load. And so I know this should be written as W2 times K22 U2 minus F2. Now, K22 is the component of the stiffness matrix for the second node. It happened to be E over L. And if I took a cross section to be not equal to 1, it would be E times A divided by L, where A will be the real cross section. And this is the external load. Here you have a BL over 2. That means in a case that you have a distributed load, you take the total load is B times L, where L is length of the bar. So on one node, you will take a half, BL over 2. On the other one, you will take BL over 2. And then you will have other contribution for this external load will be the following. You will have a T bar applied in the second node. And then basically you have a contribution from the imposed displacer that comes naturally from this type of computation. So if I divide F2 by K22, I obtain directly the value of displacement which is equal to U bar plus T bar L divided by E plus B L square O2E. What's miraculous is the strong form solution that's precisely the same value. In other words, what we obtain by doing this is we obtain something that is called superconvergence. The value of the displacement, nodal value of the displacement or the real field is the same in strong and in both in the weak form. This is really a remarkable result. And not only displacement, I can also show that if I now compute the displacement derivative, please note here they're constant, because if I take a linear interpolation of my displacement, which is written up there, this was my linear interpolation of displacement, I take derivative, of course I'm going to get a constant term. So now this is not the same as my linear interpolation of the strain field, which I was computing before. Here it is that your linear interpolation of the strain field when I have a strong form, but this constant value is matching the true variation precisely at the center of this bar. So I have actually the nodal values of the displacement and the midpoint values of rapid stress for the strain and also stresses to be exact. And this is something which is really remarkable for 1D problem. This is called a superconvergence type of thing. Please note that when we applied for this result, both in strong and weak form, we have applied these essential boundary condition and natural boundary condition we recovered. So the fact that these displacements are matching at the nodal values, that means at the ends of the interval of the bar, this is first remarkable result, and the fact that the stresses and strain are matching at in the middle, it's also another remarkable result. These are so-called Barlow points, and all these values are called superconvergence properties. In other words, if you want to get an illustration, I want to invite you to really control that. You'll get something like this. You will get basically there's a solution to the weak form. Sorry, something, let's say, solution to the strong form. So this is, let's say, your solution. Let me, something that this is implies displacement that goes like this. Solution to the weak form will not be that, but will be something like that. So this is something that you call U. Up. And oops, and this is something that you call U of H. Up. Not perfect. Anyway. So basically, these two values at the end of the integral are the same. Also, the slope of this thing and the slope of that thing, so it's not very nicely written, it should be the same slope, is the same. And this is precisely what these superconvergence properties should imply, basically. So that comes from that could be shown in this book. There's something to prove that from error estimates and so on and so forth. So I'm not going to dwell on that. Now, if you have nonlinear elasticity, the problem is a little bit more complex in the sense that you cannot go that in a single shot. So structural solution is not possible to obtain other than just stresses. I couldn't obtain displacement because basically I was not able to do it. It was too complicated differential equation. I didn't spend enough time. If you manage to do it, so it's not perfect. But the weak form I can obtain without any problems. Again, I do the same interpolation. What change the interpolation are the same shape functions. If you say 1 minus x over L and x over L, and I then use imposed displacement, I use the kinematic admissibility of the virtual displacement, I kick out this guy. And at the end, what I have here is a nonlinear equation that expresses equilibrium in terms of displacement. I can again reason this equilibrium equation should be valid no matter what's W2. So at the end, I get to something which is quadratic equation in terms of U2. And that's why I chose it as a quadratic constitutive equation for nonlinear elasticity, because it's one of these cases where I know how to obtain the solution directly. If I assume that all the forces are positive, that means the bar is in tension. I will know that the only solution that is acceptable is the U2 to be, positive part of that one. Otherwise, you have two solutions. And so this way I can get the true solution by the weak form. Now, obviously, for any other more complicated problem, I cannot obtain that. So that's why you go into the how this technology of the finite element is working, and discuss really the methods that are used in this software directory. So please let me know if I can answer any question before the break, or if you have any comments or stuff like that. Huh? I assume that this should be kind of introductory material that you have seen probably in this or that manner in already a number of previous cases. But nonetheless, maybe let's say it's still it's worthy to it's worthy to take it in more detail. So basically, if you have no questions, let us take a break until 12, and we get another session on this one. Do you have any questions? Any comments? Everything is fine? Perfect. Then okay, let's take a break until 12 o'clock, and we get back together at 12 to finish this one 1D case perfectly. Okay? Okay. Talk to you in 12. Bye-bye.